Okay, this is section 4.3, video 2. So we have talked about the fundamental theorem of calculus part 2. Now we're going to be talking about the fundamental theorem of calculus part 1. We're going to use part 2 to kind of show how part 1 works. Okay, so part 1 basically says that if you have a function which is defined as an integral, then if you take the derivative of both sides of the function, you're going to get out a special result. And we're going to show that specifically here. So the first part just says find the integral. Okay, so there's no derivative here. We're just going to find the integral, which we can do. Because our fundamental theorem part 2 says take the antiderivative first. So that would be 1/3 t cubed plus t squared. That's the antiderivative of t squared plus 2t. And then evaluate that at your bounds. Okay, just because we have a variable in the bounds doesn't change anything. We plug in the upper bound first. So we're going to get 1/3 x cubed plus x squared. And then we're going to plug in the lower bound and we'll subtract it. So we're going to get, let's see, 1/3 times 2 cubed is 8/3 plus 4. And I'm actually going to leave it like that, and you'll see why in a second. But that would be the integral. Now the next part says what we want to do is we want to take the derivative of the integral we just found. This is what we just found, because that is this right here. So that means I want to take the derivative of all of this. So if I were to take the derivative of what's up there in the big bracket, well, let's see. The derivative of 1/3 x cubed is, bring the 3 out to the front, reduce it, you're going to get x squared. The derivative of x squared is 2x. And the derivative of everything that's left over, because they're constants, are 0. So that's it. We get x squared plus 2x. So that is the derivative of the integral that we just found above. And again, what I want you to see is, what did we really just do? What we really just did was, if I were to take the derivative of this integral, I literally just took the x's and I plugged them in where the t is. Because now you can see you would have x squared plus 2x. Okay, let's do the same thing. So we're going to find the integral from, this time from x to 4 of the square root of t dt. So remember, the square root of t is t to the 1/2. So when I take the antiderivative, it's going to be t to the 3/2, and then dividing by 3/2 is multiplying by 2/3, and we're going to evaluate that from x to 4. Again, always plug in the upper bound first. So we're going to get 2/3 4 to the 3/2 power minus 2/3 x to the 3/2 power. Okay, and this is our integral. Now the next step says find the derivative of that integral that I just did. So I'm going to take the derivative of what I just kind of boxed in up there. Well, the whole first thing why I didn't simplify it is because that's just one big constant, so that's 0. Minus, if I bring the 3/2 out to the front and multiply it by the 2/3, I get 1x to the 1/2 power, reducing the 3/2 by 1. And of course, x to the 1/2 is the square root of x, so really what I get is the negative square root of x. And you might say to yourself, well, wait a minute, that's close to what we just did. It is, because again, look what happened. I took the x and I plugged it in where the t was. Well, that should have just given me the square root of x. The reason it's a negative square root of x is look where the x was in the integral. The x was in the bottom bound. Okay, so hopefully that's what you're seeing there. That's what you're noticing, what kind of a pattern there is. So the second one had a, let's not put a minus sign, let's actually just write it, a negative, because the x was in the lower bound. Otherwise, you're still just plugging in x. All right, so why would we have to do this? What is the purpose of doing this specific derivative of the integral and stuff like that? Well, like I said, you can use part 2 if you can take an antiderivative. Maybe there's certain things that you cannot easily take an antiderivative of. For example, at this point, you do not have a method to take the square root of t squared plus 1's antiderivative. There are ways to do this, but in this case, you would not know how to do it. So if I take the derivative of that integral, it just says I'm going to take the x and I'm going to plug it in for the t. So really, the derivative of this integral will be the square root of x squared plus 1. Done. That's it. Okay, you don't have to try and take the antiderivative, plug in bounds, and then take the derivative again. That's the shortcut. Okay, same general idea number 7. Look where your x is, however. It's in the bottom, so the first thing I'm going to do is I'm just going to throw a negative sign out in the front, and then I'm going to plug in the x. So we're going to get x squared minus 2x plus 5. And technically, that's the answer. If you want to distribute the negative because you think it looks better, then negative x squared plus 2x minus 5. Either one is perfectly acceptable. But that's all we had to do. You just plug the x in for all of your t's. Okay, now again, this is the way it is if it's as simple as just x. It won't always be that simple, as we can see here on the next page. So we're going to do the same process. What you should see now is one of my bounds as 5x. It's not just x. I want to find the integral of secant squared t dt. So I'm going to take the antiderivative. Hopefully you remember that the antiderivative of secant squared t would be tangent of t, since the derivative of tangent is secant squared. So this is going to give us tangent of t, and we're going to evaluate that from 2 to 5x. All right, so that's going to be, plugging in the top bound, tangent of 5x minus, plugging in the lower bound, tangent of 2. Not going to evaluate tangent of 2. There's really no reason to do that, because the next thing says, now let's take the derivative of what we just found. So we are going to take the derivative of this. And the derivative of tangent of 5x, we have to incorporate the chain rule here, is going to be secant squared of 5x times the derivative of the angle, which is 5, and then minus the derivative of tangent of 2. Tangent of 2 is a constant, so that's 0. So the biggest takeaway from this one is that the bound was not just x. So what we do is we take this, plug it in for the t, same thing, but then we have to remember to multiply by the derivative of the bound, which in this case was 5. Okay, let's try again. As a matter of fact, let's not do the long process. Let's just go straight to this step right here. According to what we just said, we take this right here and we plug it in for t. So that's going to give us cosine of 2/3 x plus 1, but then we have to remember to multiply by the derivative of the bound, which is just 2/3. That's it. Probably want to rewrite it as 2/3 and then cosine of the angle. So when there's something other than just x, you have to multiply by the derivative of the bound. Okay? And that's the what do you notice part. We must multiply by the derivative of the bound. And technically that's what we were doing when it was just x as well, because the derivative of just x is 1. So we would always have been multiplying by 1 anyway. All right, so let's try a couple more. Again, I'm going to take the bound. Since it's on top, it'll be positive. Plug it in for the t. So we're going to get the cube root of 8x squared, but then don't forget to multiply that by the derivative of 8x squared, which is 16x. I don't have to worry about the lower bound because there's no variable in it. The whole thing's going to go to 0 when we multiply it by the derivative. Yes, this could be simplified because I can take the cube root of 8 out. So that would actually be, the cube root of 8 is 2. So I can multiply that by the 16x and get 32x cube root of x squared if I want to. I could rewrite the cube root of x squared as x to the 2/3 and multiply that by the x. There's no reason to do all that, but you could do all that if you needed to. Okay, we could check. I'm not going to run through the check on this one, but you could check by doing the antiderivative process and then taking the derivative again. No need to check. No need for me to go through that. Does it work? The answer is yes, it does. All right. So the last definition, this is probably the more apt definition because it covers everything. If I take the derivative of the integral, where each one of the bounds, because you could have both bounds as functions of x. Doesn't just have to be one. Both of them could be functions of x. So I've got h of x in the lower, g of x in the upper. You plug in g of x, so you plug that one in, and then multiply by the derivative of the bound. That's this piece right there. Then you plug in h of x, and then multiply by the derivative of its bound right there, and subtract. That's the fundamental theorem of calculus, part 1. But you have to be taking the derivative of the integral with variables in the bounds. All right, so let's go ahead and see what examples we've got there. All right, so the first one says take the derivative of that integral. We have the x cubed in the top, so all we do is plug in the x cubed for t, but then don't forget to multiply by the derivative of x cubed, which is 3x squared. That's it. That's the derivative. Don't worry about the pi halves because pi halves is a constant. It's going to go away. Okay, number 11 is a little bit more tricky. You got to be careful here on all your signs. That's why it's tricky. So taking the derivative says plug in the x first, so x cubed, times the derivative of x, which is 1, so I could technically write that, minus, plug in the lower bound. Now you got to plug in negative x and cube it, times the derivative of negative x, which is negative 1. So there's a lot of negative signs rolling around here. So really what we get is x cubed minus negative x cubed cubed is still negative x cubed, times a negative 1 is positive x cubed. So really what I have is x cubed minus x cubed, which is 0. Now, if you really think about this, let's sketch the drawing of this one. T cubed looks like this. So if I was to go from negative x to positive x, it's the same distance left and right, negative x to positive x. The area between the curve and the x-axis here, and the area between the curve, and I've kind of missed, and the x-axis there is exactly the same. One positive area, one negative area, adding those together, they will cancel each other out and give you 0. Now this works for odd functions because t cubed is an odd function symmetric to the origin. So as long as you go from the same left bound to the same right bound, you're always going to end up with 0 for an odd function. All right. Oh, that was the last one on that page. Okay. So then there's some mixed problems on the back here. I will walk through all these with you guys just to show you some of the different things that are going to happen, some of the things to look for. So if we were to take the derivative of the first one, notice we have x's in both of the bounds, so we have to include both of them. So the first thing is we're going to take that and we're going to plug it in for t. So we're going to get 4 times 3x plus 2 plus 1. I have to multiply that still by the derivative of the bound, which is 3. Make sure you put that whole thing in parentheses, otherwise you might forget to multiply every piece by 3. And then minus, now we're going to take the x and plug that in. So we're going to get 4x plus 1 times the derivative of x, which is just 1. So then we could go ahead, distribute everything, simplify it all down. I think when you do that, I'm not going to walk through the whole process. I believe you get 32x plus 26. I believe that that's the final answer. You guys can check that. All right, you might look at number 13 and say, well, wait a minute, that doesn't look the same. You're right. This is just an integral. That's why it says mixed problems. We're not taking the derivative. We just have to find a way to integrate this. Well, we also don't know how to do anything with quotients yet. So in this case, we actually have to do something to simplify this. Well, you kind of have to remember your trig identities. 1 minus sine squared of theta just happens to be cosine squared of theta. So what you really have here is the integral from 0 to pi fourths of cosine squared of theta over cosine squared of theta d theta. But of course, cosine squared over cosine squared is 1. So what we really have to take the integral of is 1 d theta. Now, keep in mind here that your variable here is theta. So when you take the antiderivative of 1, it's not x, it's theta. And we're going to evaluate that from 0 to pi over 4. If I plug in pi over 4, I get pi over 4. If I plug in 0, I get 0. So the answer is pi over 4. All right, just a few more to go. So in number 14, we are taking a derivative of an integral with a variable in the bounds with sine of x. So again, we're going to take the bound, plug it in. So we're going to get the square root of sine squared x plus 1 times the derivative of sine, which is cosine, and then the lower bound is 0, so we don't have to worry about that one. So that one's done. Okay, number 15. Number 15 you have to be really careful about. Usually when I do this one in class, I give everybody some time and everybody comes up with all these answers. Remember that in order to do this, something way back in the beginning of the videos, these functions must be continuous on the interval. 1 over x squared is not continuous at 0, and 0 is in between -2 and 2. So we cannot take this integral from -2 to 2 because it passes through 0, and 0 is undefined. So in this case, we would simply say it is discontinuous on the interval from -2 to 2. So the fundamental theorem of calculus fails. It will not work. Now there is a way that we can actually figure out much later on at the end of the course whether we could actually have an integral for this, but for right now, fundamental theorem of calculus will not work. So you do have to watch for your intervals of continuity. All right, in number 16 is relatively straightforward. Got an x in the bound here. We're taking the derivative, so we'll plug the x in for all the t's. X squared plus 1 times the derivative of x, which is 1, so I don't have to write that. So that one's pretty much done. Number 17, we are not taking a derivative of an integral. We're just taking an integral. So we need to use the antiderivative technique if we can do it. Well, the antiderivative of 2 is going to be 2t. Antiderivative of negative cosecant squared of x is going to be positive cotangent of x. Oops, cotangent of t, sorry. And we're going to evaluate that from pi fourths to pi halves. So we'll have to be good at our trig values here. So first of all, plugging in pi halves. 2 times pi halves is just pi. And then cotangent of pi halves. Remember that cotangent is cosine over sine. Cosine of pi halves is 0. Sine of pi halves is 1. So 0 over 1 is 0. Minus 2 times pi fourths is going to be 2 pi fourths, or pi halves, plus cotangent of pi fourths. Again, at pi fourths, it's cosine over sine. Cosine of pi fourths is root 2 over 2. Sine of pi fourths is also root 2 over 2. So when you divide the same things, you get 1. So cotangent of pi fourths is 1. So ultimately what we get out of this is pi minus pi halves, which is pi halves minus 1. Okay, and one more to go. Again, this is just an integral. It's not a derivative. So we're going to take the antiderivative of 2m, which is m squared, antiderivative of cosine, which is sine of m, and we're going to evaluate that from negative pi halves to pi halves. Plugging in pi halves first, we are going to get pi squared over 4. That's plugging it into the m squared. That should be a squared. Pi squared over 4 plus sine of pi halves, which is 1, minus plugging in negative pi halves. Squaring negative pi halves also gives you pi squared over 4. And then sine of negative pi halves, that's in the same location as 3 pi halves, so that would be negative 1, so minus 1. All right, so let's see. Pi squared over 4 minus pi squared over 4, those are gone. And then I get 1 minus minus 1, so we get 2. All right, that should do it for this video. That should do it for this lesson. You have plenty of examples to go by, so hopefully some of the algebra and stuff in there isn't going to be the thing that catches you on this. But again, this is an extremely important lesson in the fact that it is the fundamental theorem of calculus. You will use this antiderivative technique and that derivative of an integral technique pretty much throughout the rest of calculus. So this is one you really want to pay attention to. All right, good luck.